Welcome to this explainer. Today, we're going straight to the heart of the absolute most complex, fascinating piece of technology in existence, the human mind. And we're going to unpack exactly how it works by comparing our biology to the hardware and software we interact with every single day. So let's just kick things off with a question that might sound kind of provocative. Are we essentially just walking, talking organic computers? Like, how much of your brain actually functions like the machine sitting on your desk or the phone in your hand right now? It's a foundational question in cognitive psychology, and the answers we have today will totally change how you view your own thinking. Section 1. Mind as a machine. To really get this, we have to rewind to a massive turning point. About 50 years ago, the invention of high-speed digital computers fundamentally shifted how we look at our own cognitive processing. Originally, these machines were just seen as these giant number crunchers, doing math in a fraction of the time a human ever could. But scientists quickly caught on that these machines could perform functions that looked an awful lot like human problem solving. And this brilliantly highlights the core difference between us and our desktop counterparts. Computers, they are absolutely incredible at pure, rule-governed logic and high-speed math, stuff that humans are honestly pretty terrible at in comparison. But us humans, we excel at forming rapid generalizations, making complex inferences, picking up on really subtle visual patterns, and, of course, experiencing emotions. Those are things computers do very poorly or just not at all. But here's where it gets wild. Modern computer scientists are actively trying to bridge that exact gap. A whole new generation of researchers are building what we call neural networks, and these act much more like our messy human brains. They can actually make generalizations and understand complex visual patterns now. But the trade-off? It's fascinating. Just like us, these neural nets are actually slower at math, and they are prone to making completely witless mistakes. And yet, they still completely lack emotions. But it really proves just how powerful the computer metaphor continues to be.
Moving on to Section 2, Core Debates in Cognition.
First up, researchers have to figure out how we actually gather our internal data. On one hand, we have rationalism. This is the idea that we discover truth by reasoning logically, relying on what we already know. It's almost like a pre-programmed algorithm running internal checks. On the flip side, empiricism argues we learn out in the real world by observing and testing what we perceive through our sensory inputs. Modern cognitive psychology usually finds that combining these two approaches is actually the most powerful way to learn.
Then we have the ultimate factory settings versus user environment debate, right? Nature versus nurture. Are the innate biological characteristics of our cognition running the show, or does our specific, unique environment shape how our minds operate? If you lean toward nature, you're looking at the biological baseline. If you lean toward nurture, you're studying those external environmental influences. And finally, there's the debate of structures versus processes. Cognitive psychologists literally have to decide what exactly they are looking at. Are they studying the static structure of the mind's files, like the contents and attributes of a thought? Or are they studying the active processing of its programs, the dynamic, real-time mechanics of how human thinking actually operates? All right, Section 3, Mapping the Brain's Hardware. Historically, much of what we knew about the brain tragically came from head traumas during wars or accidents. But neurologists, like Carl Lashley back in 1929, were wrestling with a massive puzzle. Is the brain holistic or localized? Basically, when you learn a new skill, is that information saved to one highly specific, localized folder in a particular brain region, or is the whole operation distributed throughout the entire biological infrastructure of the brain? Section 4, the cognitive science convergence. So the really crucial takeaway here is that cognitive science isn't just one thing. It's this powerful cross-disciplinary convergence. You've got computer science handling AI and computational models. You have neuroscience mapping out the actual structural anatomy and biology of the brain. And you have cognitive psychology looking at the mental phenomena, perception, memory, language. The boundaries between these disciplines are totally blurring, and by teaming up, they are radically transforming how we understand our own species. Section 5, Real-World Applications. Now, researchers face a constant balancing act when testing all this. Highly controlled lab experiments are awesome because they increase the probability of valid causal inferences, meaning you can prove exact cause and effect. However, naturalistic techniques give us what we call ecological validity. By observing behavior out in the wild, researchers get to see how our organic hardware actually performs when it's not locked away in some sterile lab. And this directly mirrors another big dialectic: basic versus applied research. Do we conduct basic research just to understand fundamental cognitive processes, like figuring out the deep underlying code? Or do we focus on applied research, which is meant to solve immediate practical problems and help people use their cognition effectively in everyday life?
Let's make this totally concrete with an everyday scenario. A perfect example of applied cognitive psychology is just a simple trip to the supermarket. Think about it for a second. Your mind is constantly processing highly engineered forms and colors designed specifically to hijack your attention. You're navigating spatial cues. You're using memory to understand the context of product labels, and you're filtering a massive influx of sights and sounds literally just to buy milk and eggs. Your brain is running an incredibly complex, real-time operating system to make it happen.
Section 6, the future of neural imaging.
If we track the timeline of cognitive study, the progression is just staggering. Centuries ago, philosophers like Pascal and Descartes were merely dreaming of computing machines. Fast forward to the early 20th century, and we were forced to infer brain function mostly by studying tragic head injuries. 50 years ago, the digital computer sparked a total cognitive revolution. And now, here in the 21st century, advanced neurocognitive imagery is driving a completely new paradigm shift.
These modern techniques, things like MRIs, PET scans, EEGs, they allow researchers to quite literally pop the hood and look deeper into the brain than ever before. What's revolutionary here is that they reveal both the physical structures of cognition and the active processes as they happen. We aren't just looking at the hardware anymore. We can actually watch the software running. Ultimately, this imagery promises to become one of the major means of investigation going forward. It's the ultimate game changer. It takes cognitive psychology from studying behavior from the outside to literally watching the engine of cognition at work on the inside.
And this beautifully reminds us of a core tenet of the whole field. It's all connected. All the basic, deep-level research into our brain's wiring may eventually lead to everyday, real-world applications. And all the applied research we observe out in the wild helps deepen our basic understanding of exactly who and what we are.
So, I want to leave you with this final thought to ponder. The next time you step into a highly engineered environment, like a supermarket or a mall, or even just scrolling on your phone, take a second to pause. Look at the colors, listen to the sounds, and ask yourself, how is your own incredible organic computer processing the world around you right in that moment? Thanks for joining me on this explainer, and keep exploring the amazing technology inside your own head.